So now we're looking at what happens if we have Velcro around these pucks, and so they're going to stick when they actually hit. Is that going to be an elastic or an inelastic collision? Still coming in at MV. And it's leaving at how fast? Well, if it comes in at MV, you have to have an MV when leaving. You absolutely have to. That's a lot of conservation momentum. I don't have any external forces like friction acting on it. But you notice it's literally going a lot slower. How much slower? Half the speed. Because if I doubled the mass, and I did indeed double the mass, that means they're both moving at half the speed the other direction. And if you want to do the math, you can. You're going to find out we lost half of our kinetic energy in that collision. So you might say, hey, where'd that energy go? Well, it's going like this. It's doing work, squeezing and pulling on these things, creating some heat energy. And that squishiness and the grabbing is where we lost our about half our kinetic energy. So that was nothing new. The new thing is what happens when they hit off center. Okay? Now they're going to stick hitting off center. Coming in like this at MV, what has to be true about the speed afterwards, and what do you think is going to happen differently? Pause and record your answer. Okay, here it is, going off center. Coming in at MV. Now you may have noticed it is indeed leaving, but how quickly is it leaving? Has to be at half the V, because you have to have the same linear momentum before and afterwards. Okay? Let me talk to you for a moment. So when hitting off center, not hitting at the center of mass of this other puck, you're actually creating a torque. And creating that torque causes things to angularly accelerate. But now the new center of mass is in the middle of this, that if you notice, if you want to go back and look at the video, it still rotates around this point, and it goes in a straight line motion. And you might say, well, how quickly does that center of mass move? Well, it has to be at half a V. Because if we clearly have an MV coming in, you have to have an MV leaving. And we clearly have two masses stuck together, so that means they're moving at half the velocity. But you notice we have, hey, don't we have some angular momentum? Why, yes, we do have some angular momentum. But that does not change the linear momentum. You still have to have the same linear momentum as before. What would happen if they just barely touch maybe? It's coming in at an MV and just barely touch the very edge. What would be different about the spins, do you think? Well, here we go. This is barely hitting the sides, still coming in at an MV. You notice there's quite a bit of spin, but they still move together at half the V. What if it's barely off center? I mean, not almost dead on, but just barely off center. Still moving at a half V, but it's barely rotating at all. Because when they're barely off center, that's a very small lever arm right there. That's not a lot of torque. When they hit way off center, that's a pretty big lever arm. That's quite a bit of torque and a greater angular motion. So, in fact, even though before it hits, this still has angular momentum beforehand that has to be the same as this, as you're seeing this, that would be counterclockwise momentum. So whatever angular momentum you start with, you also have to end with.